yesterday, as you can see that on the definition of the sorption time, I have told you that the sorption time is defined as the time required to dissolve or adsorb the 66% of the total gas adsorption from the coal core or from the coal sample. Okay, but it is slightly modified. It is not correct. It is related to the 63.2%. Okay, it is related to the 63.2% of gas dissolved from the total gas which is inside the coal. So sorption time is related to the 63.2% of the total amount of the gas dissolved, the time required to dissolve 63.2% of the gas from the coal sample. Okay, and this is generally measured from the field desorption canister testing. That means in the field, whenever you are collecting the coal samples, immediately after you are removing the coal barrel and you are taking the coal sample, you are going to put into the desorption canister, which is already having some pressure gauge fitted to it. So as you are going to take out the core from the core barrel, so you are releasing it to the atmospheric pressure from a very high pressure, and then the gases will start to dissolve. If you are not going to take those gases, you will not be able to get any estimation for the lost gases. As you know that there are three components. There is a lost gas, adsorbed gas, and the residual gases. To get the complete idea about the gas storage capacity or the gas content of a coal. So that's why you have to know three independent parameters very accurately. Otherwise, you will not be able to predict. Okay. So yesterday we have also discussed about the relative permeability. Okay. When the relative permeability is coming, you know that whenever the production is taking place, and the first place there is only the gas production is coming. Okay, there is first, in the first case, as you are going to take out the water, only water will be coming out. Okay, as the water is going out, so the reservoir pressure is going to reduce, and so the gas is going to dissolve. So at some point of time, there is in the production, there is some fraction of the gas, there is some fraction of the water also. But then, as these are the two different phases, only it is not the permeability of the individual phase. That means it is not the water permeability or the gas permeability, which is coming very much important for the fluid flow, for the Darcy flow, if I say correctly. But it is also the relative permeability between these two phases, because at the border of the water and the oil and the gas layer, there will be always some resistance, because the viscosity or because of the different properties, because of the different quantity per second which is flowing per time through a channel. Okay, so this relative permeability is becoming more important whenever there is a two or more phases. So that has to be taken into consideration. Okay, now continuing this discussion, we'll be moving into the factors which is going to dictate, which is going to be important for the well productivity, that control the well productivity. Well productivity means the borehole, the gas production well is there, and how much production you are going to get, how much recovery you are going to achieve. Okay, how much recovery of the gases you are going to achieve, or the coal. Okay, so now if you see a typical production graph, let me show you first the figure 3.7. Please see figure 3.7. This is the typical production graph from a borehole reservoir, from a CBM reservoir, okay, of a single well. You can see in the x-axis they have put the time, in the y-axis they have put the production rate in MSFD. Now when there is only 1 M, it is 1000 standard cubic feet per day. Okay, when there are 2 M, it is million. Let me remind you, when there is only 1 M, small or capital, it is only 1000 standard cubic feet per day. It is referred to 1000. When there are 2 M's, it is referred to as million. Okay, So you can see in the y-axis, the fine line is giving you the water production graph, and the dotted line is giving you the gas production graph. And you can very well see that there are three different individual phases with different gas and oil production characteristics. So that is the thing we need to know. In the following discussion, in the discussion that coming after this heading, you will see that that they have given in the paragraph, they are in the following paragraph, they have discussed this. Okay, you can see the phase 1, and then you will see the phase 2, and then phase 3. Okay, they have discussed each of this thing in a more detailed way. So I am going to discuss this thing in a brief way, okay, for you, and you have to read it accordingly. Okay, if you have understood, if you have any confusion, you will contact me in the next class. Okay, so you can see the phase 1. What is the phase 1? Phase 1 is, you can see the phase 1 is differentiated or defined by a constant rate of water production. This is the phase 1. This is the small amount. Okay, what is happening? Suppose a coal bed methane reservoir is there at some depth. Okay, the coal seam is situated at some depth, and there is already water poured into it. So obviously water pressure is also staying there. Okay, now you have connected with or the reservoir through a borehole, you have put a pump, and now you are going to take out the water at a constant rate. So Q is constant, meter cube per second. Q, water production rate, volume. Okay, it is constant. So now it is a standard cubic feet. So you can see that while the water production is the constant, it is constant, it is parallel to the x-axis. That means with time there is no change of the water production rate, but this production is the highest one, because as you are going reducing the pressure, obviously the water will be coming out. Okay, suppose you are putting on the turning on the machine, and within a very few fraction of the second it is reaching it is operating in this normal, suppose in 1000 rpm it is running. So the time required to reach 0 to 1000 rpm may be very few seconds. So at that point the production will be increasing from 0 to some limit, and then when it is reached a constant rpm velocity, the motor is running at constant speed, then the water production will be also constant. Okay, so you can see that there is a very small part, okay, which is given by the constant water rate. Okay, this part is the constant water rate, and see that this is called the phase 1. Phase 1 means it is defined by the constant water production rate. Okay, and then the water flow, the declining pressure, the bottom hole pressure is going to reduce, because whatever was the total pressure, as you are taking out the water, so obviously pressure is going to reduce, reservoir pressure is going to reduce. Okay, as the reservoir pressure is going to reduce, you can see that gas production is started from 0. This is the gas production. Gas production started from 0, and it is continuously increasing, steeply increasing with this phase 1, within this phase 1. Okay, that means that depending on the rate of quantity of the water is producing, water production rate is constant. But as the pressure is going to reduce very sharply, because you are taking out the water at a constant rate, so obviously the total pressure of the reservoir is going to reduce very quickly. And whenever the pressure reduction is very quickly, so that means the gas desorption process is going to happen very much quickly. So that's why there in the very fast phase, you can see that the gas production rate is very quick. Okay, it is steeply increasing, so gases are coming out. At the end of the phase 1, you can see that the gas production rate is more or less, it is steeply increasing, and then water production step is also constant. Then after, when you have reached the end of the phase 1, the well has reached its minimum bottom hole pressure. Bottom hole pressure means the pressure at the seam or at the reservoir, at the end point, at the bottommost point of the borehole. That is called the bottom hole pressure. So obviously, as more and more number of water is going to be reduced. So obviously the bottom hole pressure or the pressure of the hole at this very bottommost point is going to be very much minimum. Okay, and then it will not be able to maintain the constant flow because most of the water has been taken out. So now the water production rate is going to less, it is going to reduce. So that is the start of the phase 2. Okay, you can see in the text also, phase 2 is characterized by the negative decline in the gas production rate. Decline means reduction, negative decline means the opposite reduction, or the negative decline means it is actually increasing. Why it is increasing? You can see that in the phase 2, see the gas production graph, it is actually increasing. Okay, this part, whatever gas production you have reached at the end of the phase 1, in the phase 2, although your total reservoir pressure is going to reduce, but then the gas production rate is increasing. Why? Because as with the total pressure, earlier in the phase 1, the total pressure part, as the water component was so high, total amount of the water is coming out and very little production of the gases are coming out. But now as the water pressure is going to reduce, and as the water quantity is also going to reduce, but your pump is moving at the same pressure. So what will happen? Now the gas will come out. Okay, so you can see that the water production is quickly reducing. Okay, it is quickly reducing. This is the decline of the water pressure graph, whereas in the gas pressure, because if the quantity, if you were earlier you were moving with 1 megapascal, you are now your pressure is also 1 megapascal, but there is a less amount of the water, so now there will be maximum amount of the gases will come out. That's why in this phase 2 there is a more gas production than the phase 1 production, and that's why it is called a negative decline, or it is a positive incline, if I say so. Okay, negative decline means it is not reducing, it is actually increasing. You can see that at the very early stage, the moment when the water is going to be steeply falling, at some place the gas production rate is somewhat becoming flat, and then again with the pressure it is going to increase. Why it is going to increase? Because of the suction pressure, and the gas quantity and the water quantity is becoming less, but the gas quantity is becoming more because the reservoir pressure is much more less, and so more and more gases are coming out. There are certain features in this phase 2. What are these? You can see water relative permeability decreases. Water relative permeability decreases. Why? Because water flow, water content is also going to decrease. Gas relative permeability increases, as you can see, because the gas flow is going to increase, because there is a number of gas molecules are higher because there is a desorption. Okay, outer boundary effects become significant, or there's a pseudo steady state flow. Steady state flow means not changing with time. It is the pressure dependent. Okay, now it is a pressure dependent process. So whatever the outer boundary effects becoming much more significant. So in your boundary you have put a channel. Okay, you have surface, you have put the pump, and water content. If the fractures are connected, it is totally connecting the gases from all the reservoir, and the gases are, and then they are going to diffuse, they are coming to the natural fracture systems, and in the free state, and from this free state, as the pump is working, it is creating negative suction pressure. So total amount of the gases from the fractured zone is going to move into the surface through the borehole. Okay, and the fourth point, as you can see, the gas desorption rate changes dynamically. Gas desorption rate, you can see gas desorption rate is increasing. Okay, more and more, because the pressure is going to reduce, and so more and more, because water, you all have the idea about the partial pressure concept. Please respond. Do you have the idea about the partial pressure and total pressure concept, different phases of the gas? Do you remember this?
Yes, sir.
Okay. So if you remember this, so suppose there is a mixture, there is an X and Y. If both of the mixture are 50-50, so obviously there may be a same amount of the fraction you can get in the production, but then their production will be varied depending on the relative permeability. But then, as in the reservoir, you can already understand that first the water totally is coming out, so the remaining water percentage will be very much less. So then in the mixture, the component of the water is becoming very much less, but the component or the fraction of the gases are becoming very much higher. So obviously now the gas pressure, the partial pressure of the gas phase is becoming much more higher in comparison to the water pressure. So as it is having high water pressure, so water is going to flow. Sorry, gas is having higher pressure, so the gas is going to flow. Okay, so the gas diffusion rates is also changing dynamically. Okay, with time the rates is going to vary. It is going to increase. Okay, like this, and it is going to reach a maximum peak point. This is the characteristics of the phase 2. You all need to understand this graph, this production graph, very accurately. Okay. And then the third phase. What is the third phase? At the end of the second phase, you can see they have mentioned that well dewatered. That means you can see that the total water production is coming very less. So whatever was the water present there, it is coming mostly fifth of the 80% of the water is going to be reduced. Only 20% water is there, and so it is assumed that at the end of the phase 2, the well is more or less dewatered. Okay, very less amount of the water will now come out, and then the third phase begins. Okay, what is the properties of the third phase? You can see at the end of the second phase, you have already reached the total gas production, the maximum gas production. How? Because you are going to, water is going to be reduced, but the gas pressure, as the more and more resorption is coming, so the gas pressure is becoming very much higher, and so with that pressure gas is flowing. Okay, very much desorption is taking place and the gas production is there. At the end of third phase, at the start of the third phase, the well is supposed to be dewatered, and you can see that the gas production is going to be reduced, water production is also going to be reduced. Why? Now you can see that after the peak gas pressure has been achieved, or the peak gas production has been achieved, mostly of the reservoir is already taken out the gases which are required, which are present at the free state. So now what will happen? With the pressure, the gas production is going to reduce because there is not much more available free gases are there. Okay, so what will happen? Phase 3 begins with the reservoir flow conditions have stabilized. So now the reservoir flow, whatever it was earlier, the steady state of the laminar flow I have mentioned earlier yesterday class, so Tuesday class. So whatever the steady state laminar flow was present, now it is going to reduce. The well has reached its peak gas rate, as I mentioned, and the gas production is characterized by a more typical decline trend. Gas production is going to reduce. Okay. During this phase, water production is very low and or negligible, and the gas and water relative permeabilities change very little. Why very little? Because both the quantities are becoming very much less. If you see the graph, both of the quantities are becoming being reduced. Okay, and you can see that the graph is more or less parallel. So at the same rate, they are going to reduce. Okay. Not at the same rate. The rate is given at the y-axis. So it is more or less with time, the rate is fixed. Okay. With time, the rate is more or less fixed at a constant rate. You can see it is gas production rate reduction is more or less uniform with time at uniform gradient. And for water also, if you can see, as the time increases, it is becoming more and more flatter. So becoming much more straight line or horizontal. Okay. So the well is considered to be completely dewatered after the end, and at the start it is more or less dewatered, and at this point the water production has reached a very low or negligible, and the gas and water relative permeabilities changes little. Okay. Pseudo steady state flow exists for the rest of the phase 3. Why is pseudo steady? Because it is not actually steady, because flow is changing with time due to reduction of the gas quantity and the water quantity. Okay. Now, whatever this production you are going to see, whatever the production length with time, okay, that means they are telling that the length of the deodoring process means this total time, okay, how much it will be. Suppose this is the length, okay, with time, in time unit they are going to produce that, okay, that this is the total length of the deodoring process, and at the end of it the water is totally coming out and gas production is coming reduced drastically, okay. So the length of the deodoring process and the magnitude of the producing rates of the gas and water are controlled by the physical properties of the coal as well as the project development parameters. What are these two? I am coming just after this. This process may take weeks, months or years depending on the properties of the producing coal bed or the coal bed reservoir properties. Okay. Now, so this is a typical reservoir characteristics for production. Okay. So now you can see I'm coming to the properties on the project design. So first, try to understand that there are three different phases, individual phases, okay, and for each different three phases there are some conditions, okay, and there are some characteristics, changing characteristics of the gas flow and the water flow, okay. So starting of this, okay, and nobody knows that at what pressure. Suppose the pressure, you can see that you can tell that, okay, no unity, no actual marking is given, okay. Suppose, let me tell you that, suppose that for this reservoir, for this graph, after reaching suppose 1 week time, suppose this small phase 1 is 1 week, after 1 week time it is going to reduce, the phase 2 is going to start it, okay. And in this y-axis also, let me tell that, okay, this maximum gas production capacity is suppose 200 MSCF per day, okay. So maybe the constant water flow rate in the phase 1 is 200. Now this is particular for a reservoir. If you are going to consider another reservoir or another borehole, you will get the same typical characteristics. The rate may be different, okay, and the time is also may be different, but the flow characteristics may be remaining the same. What does it mean? It means that the characteristics of the water and the gas and the reservoir may be the same, but it will not exactly matching with the other reservoir time and the production, because there are certain variable, controllable and uncontrollable parameters. Okay, easy to understand? So if you are going to get in a simple CBM reservoir, if you are going to put 3 boreholes, the 3 boreholes production graph will not be exactly the same. It may be exactly of the same nature. There may be a possibility that all the water and the gas production graphs are more or less of the same nature, same graph, but they may not be of the same magnitude and same time frame. Okay. Now let us see to the properties. What are the properties? And obviously, if there is a very much differences of the governing parameter, even if you are taking the 3 boreholes in the same CBM reservoir with not very much a distance apart, then also you may find that the 3 borehole production characteristics may be different depending on the certain features. Okay. Now come to the physical properties. What are the reservoir physical properties? The reservoir physical properties are obviously some of the properties for the, as I have mentioned earlier, that the coal properties and the reservoir properties together, the reservoir conditions. So let us see. The first is the spacing and continuity of the fracture system, which are quantified by the permeability. Spacing, how frequently the fracture system network is there, face slits or the butt slits, okay, or the tertiary slits, and continuity, how much extent they are, whether they are going to interconnected or not, they are going to intercept with one another or not. So both of the things are important, okay. And why the fracture system is coming first? Because permeability is defined through the fracture. It is allowed through the fracture. Remember that it is a dual porosity and single permeability. Dual porosity means, dual porosity, the primary porosity is of the macropores and macropores mesopores, and the secondary porosity is for the natural fracture systems, whereas the single permeability is only through the fracture system. There is no permeability or the fluid flow is allowed into the pores, but only diffusion is allowed through the pores. Diffusion is not pressure dependent, diffusion is concentration dependent. It is totally different phenomena. Okay. The second point, the amount of the gas stored in coal organic material which is quantified by the adsorbed gas content. That means the amount of the gas stored in the coal organic material, the composition, the grade, the type, the rank, everything is coming here. Depending on the type, rank or grade, you know that their composition will vary. Some of the coal will have very high capacity of the carbon content, more than 90%. So you are supposed to get a very high gas content if the rank is also, because you have already seen that if the rank is higher, so obviously it may deliver some higher content of the gas. Whereas if you see that a particular type of coal is having very high moisture percentage or high volatile content or high ash content, obviously its corresponding carbon content will be much more less. It will be not very much high grade. It will be not of very much high rank coal. So obviously it is going to affect the gas content. And so its production graph, when you are going to see the coal production graph, the gas production graph from that reservoir, obviously you may find some changes. But then also let me tell you, the three different phases may be present, but their extent and the shape of the graph may be changing. Okay, the three different phases may be present, but their shape and the extent may be changing. The third point, the interactions between the gas, water, and the organic coal matrix, which are quantified by relative permeability and the capillary pressure. Capillary pressure, I think you know, all of you know, depending on the fluid mechanics class. If you don't know, I request you to just search over the internet to get what it means. Okay. Capillary pressure and the interactions. Interaction means now there are three phases are coming. There are two phases of gas and water or the fluid. Okay, together they are mixed and termed as a fluid. But again, there is a solid coal structure. Now, how these three will work together with one another or in the combination of the other, and with how their properties will be compatible or not, how the gas particles and the water particles will move, whether they will be changing in the viscous forces, they'll be changing in the density, obviously their property will be different. So with that differential property, how they are going to move into the fracture system. Now imagine that there is a oil part, there is a gas particle, there is a water particle. Okay. Now the particle size, the diameter of the particle can vary. The viscosity, when it is moving, the viscosity of this gas and water will also vary. The compressibility, I hope you understand, it is related to the bulk modulus. It is the volume expansion with the pressure. So with water and the gas, you know that the gas compressibility is very high compared to fluid, compared to liquid or the solid. So that is also coming into the picture. And then obviously the capillary pressure, or if you say so, the pressure is already there. So obviously the production is going to be changed. Okay. In the fourth chapter, we'll go each individual parameter. So if you have not understood at this point of time, don't worry. The fourth point and the last point is the propensity of the coal organic matrix to release stored gas, which is quantified by the diffusion coefficient and the resorption isotherm. That is very much important. Propensity of the coal organic matrix. We have seen that there is a solid coal matrix which is surrounded by the face slits and the back slits, which are the natural fracture systems. are mainly stored into the pore network, in an adsorbed state, which is different from the free state and which is stored under the pressure. Until unless you are reducing the pressure, you cannot take out the gases. The gas cannot move out automatically. Okay. So, how a cold matrix will behave with the concept with pressure decline. Now let me tell you, you have studied rock mechanics. You know that coal can be also taken as an elastic body, and for each elastic body, you know that there may be a stress strain graph, there may be a elastic limit, there may be a fracture, peak stress, and there may be a failure. Okay, so at some point you know that for each of the material there is an elastic limit. That means if you are applying the pressure, it is going to deform, it is going to be contracted. If you are removing the pressure, it is going to return to its original state. That is within the elastic limit. Now, when the elastic limit, you exceed the pressure beyond elastic limit, what will happen? There will be a permanent set, there will be a deformation. Okay, but then before failure, any material will be taking its peak load. Okay, it will be taking a peak load, and then only it will fail. When the applied load is much more higher than the load what it can withstand, the material will fail. Similarly for coal also, depending on its compulsion type and rank, okay, its strength will also vary. So now, whenever the storage gas is there, okay, you know that whenever you are taking out the water, you are actually reducing the pressure. Now imagine a coal at the underground, which is surrounded by the other solid coals in the sides, and there is a overburden pressure also, vertical load, and there is a in the bottom also. So it is totally confined. Okay. Now imagine that if a coal block is confined or whether it is not confined, the strength or the pressure, will it be same or not? Can anybody tell me that whether a similar rock body is going to show you the same type of strength, same strength magnitude when it will be in confined or it will be in unconfined position?
No, sir.
Why it is no? What will be more? In what case it will be showing more strength?
If it is in confined state, it has more strength, sir.
Why? You have studied rock mechanics, that's why I'm asking. Why it is so? Can anybody tell me why in confined case, the strength of the body, strength of a rock is increasing?
Because of the confinement,
Yes.
one direction movement will be restricted, so that
Okay. If it is confined, whenever you are going to apply the pressure, it is having no space for displacement. Okay. It cannot move in the sideways. At the same time, whatever the apertures or the fractures are present inside the coal or inside the core, the microcracks, the microcracks are also closed, so it is becoming much more packed or the compact, and obviously it is going to give you much more strength, much more strength, because you are compressing and it is in the inner part, it is becoming more strong. Okay, so that's why it is already having as you are surrounding by the other coal samples, other coal, it is going to exert the pressure, so it will be much more strong, much more strength it will require to break. So that's why this when it will be under the pressure, okay, it may also deform, as coal is the elastic body. So suppose a chunk of coal is going to deform, what is going to happen? Imagine, you have to visualize. Suppose a coal block which is 1 centimeter cube, okay, you are applying pressure, Okay, confining pressure in triaxial load. Okay, so what will happen? It is going to shrink. Okay, it will be contracted. When it is going to be contracted, what is happening to its fracture? Its fractures are also going to be locating close to another. It will be trying to come close to one another. What does it mean? The open channels, the permeability is going to be reduced. Okay. If there is a micro cracks, first the micro cracks will try to close, and if there is open cracks, obviously that will also try to close. So in a nutshell, the permeability is going to be reduced. Now, whenever and again in the permeability in the open channels, if earlier there was some water or fluid present, so at that reservoir pressure, obviously that water or the fluid will be also having some pressure. So you cannot remove that water or fluid from there. And if you are going to shrink it, if you are going to apply the outer pressure, that water pressure is going to exert. So that's why the effective stress principle will come. Okay. So whenever there is a pressure, there's a reservoir pressure changes, the coal chunk or the coal body is also supposed to contract or expand. And similarly, the fracture systems or the pores are also trying to expand or contract. So imagine that when the gases are stored or the gases are releasing or gases are flowing through the open channels, with this contraction and the expansion, how it is going to affect the production? Obviously, it is going to affect, because if the pore spaces are becoming very small, so the adsorption space or the volume adsorbed will be also less, because the pore is becoming smaller now. If the pore is becoming higher, then the opposite same. If the aperture is going to close to one another depending on the water pressure, depending on the surrounding pressure, what will happen? The Q, meter cube per second flow, the quantity flowing per second, which is going to increase the permeability, that will be also less. So in that case, from the same coal as coal, you are also going to get the very less production. Now mind that less production does not always mean that there is a less gas content or the less gas stored. It may happen that the gases are stored, but due to some problem, the permeability is going to be blocked or reduced, and so you are not getting the up to the mark production. You are getting only some part of the production. Okay. So the interaction of the gas, fluid and the coal is very, very important. And so this is going to be identified by the isotherm graph, which is going to show you that with pressure, how much gases are stored, gases are to be adsorbed or dissolved, which is given by the isotherm. And then the diffusion coefficient. What is diffusion coefficient? Diffusion coefficient will give you the idea that with concentration gradient, okay, with concentration, with unit point of time, how much gas molecules are going to be transferred from one layer to another layer. And until diffusion happens, okay, the permeability cannot start. It is first the desorption and then the diffusion. Desorption, the pores, the state gases are coming into the free state. Okay, the gases are dissolved. Now, from the pore wall boundary, they will move to the fracture system boundary. So now they will come from the pore to the fracture system. So they have to cross a layer, that is diffusion. Okay, so the diffusion coefficient will come into the picture based on the concentration depending process. Okay, and then with the pressure, it is the Darcy flow. So until and unless these two processes, disruption and the diffusion, are going to happen, you are not going to get a good permeability or the good Darcy flow, and you will not be able to recover very high amount of the gas production. Okay, this is the reservoir properties. Now, let me just tell this project development properties. Some of these are very important concepts. That's why I'm going to be very slow at times. Project development parameters means how your design, how your project is situated. That means if you see the figure 3.8, okay, let me show you the 3.8. you can see the effect of the interference and well pattern on the coal bed methane recovery. Okay. In this case, they have taken 9 borehole in a grid pattern. You can see there are 9 boreholes. Okay, in a grid. Now tell me, if you are having, you have done the rock excavation, stresses around rock excavation, you have considered a single borehole. Imagine that there are 3 or 4 boreholes. So obviously there will be stress changes, there will be some disturbances, there will be a local stress and the global stress concept. There will be a near stress zone and the far field stress zone. There will be a zone of influence for one borehole or 2 borehole or all the boreholes taken together. Do you understand my points, whatever I am discussing? If you compare,
Yes, sir.
yes, if you compare this consideration with your rock mechanics class stresses around mine excavations, you will be able to understand. So if I consider that, okay, there is not only one borehole, or suppose there is, if there is one borehole, then whatever production is coming, that will be totally based on this production parameters. The depth, the width of the borehole, the bottom hole pressure, the surface borehole pressure, the wall of the borehole, how, whether it is present or not, whether there is any fracture in the side so that gases are not coming out, it is going to be cross flow. But then, if I am not taking only one borehole, if I am going to take, suppose one central borehole and 4 corner boreholes, suppose 5 boreholes, okay, or suppose I am going to take 9 boreholes, then obviously, if you are going to consider the production from the central borehole, the other borehole presence or the other borehole properties also, it is going to be affected, or other borehole parameters are going to affect your production from the centralized borehole. Why? Because all of these are very much connected. Because coal is a very fractured rock, and again, if you are going to produce a borehole, its effect, the moment you are going to drill a borehole, you are going to induce the fracture. Some of the rocks are totally fractured, it will fail, and up to certain zone from the boundary of the borehole into the rock, there will be certain fractures. So it is not an intact rock case. There will be a rock mass case. As you move from the central of the borehole, central point of the borehole to the inside the rock, after some 3 or 4 times of the borehole diameter, you will find that there is no such disturbances. But then this 3 to 4 times of this distance of this borehole may be significant, because in the other part there is another borehole lying. So it may happen that the 2 consecutive boreholes, if you are considering borehole 1 3 times of the depth of the borehole 1 in the right side, and you are considering for the second borehole 3 to 4 times of the borehole there to the left side, you may find that the zone of influence of this 3 times to 4 times of their diameter may superimpose, may overlap. It may also happen that they don't touch one another, they don't overlap one another. In that case, your position, the separation of the borehole is going to be important. And as your strength parameter is going to vary, this parameter, this production parameter is also going to vary. So whatever parameter you have discussed, you have seen earlier, density, porosity, the isotherm, the reservoir properties, okay, the depth, the stress condition, the permeability, relative permeability. It is not only for this particular borehole, you have to again see that what is the condition lying in the other boreholes. It may happen that this particular central borehole, whatever porosity or the permeability it is getting, the other boreholes may not be having that much of permeability. There may be a fissure zone, there may be a barren zone, there may be a different type of the layer, rock layer is present, because it is underground and you don't know. Okay, because the coal bed methane reservoir well can go very deep. It can go as high as 2 kilometer or 3 kilometer, maybe depending on the deposition. Okay, and depending on the technology available to you. So like that, you can see that in the x-axis they have given isolated. Isolated means only single borehole. 3 spot, 3 borehole, 5 spot, 5 borehole, and then shielded. Shielded means your one borehole and you are totally shielding this area, okay, or maybe the 9 borehole and you are giving a cover, you can see in the diagram. And in the y-axis they have put recovery from the interval area, gas in place, GIP is the gas in place, how much you are going to recover. So now you see how much gas you can recover, this is the way. So obviously that if you are going to put a single borehole and you are going to put a 3 or 5 number of boreholes, your gas production will increase, okay. But then it is not always the case that the rate will increase, but not systematically, not with the total year, okay. It may happen that first 5 year it may increase and then sometimes it may decrease, that is a different issue. But to show you the what design or the effect of the project reservoir properties or the project development guidelines, that means how you are going to design your boreholes, okay. So what other, if I tell you in that case the other parameter, what happened, yes. So if you see the other parameters, what are these? The degree of well interference, as I have talked, the zone of influence, and consequently methane recovery rates from each of the boreholes are affected by permeability, the degree of well stimulation, this is a new word, I am depicting it, I am describing it right now, hydraulic fracture dimensions and the well spacing. Spacing I have already mentioned, because depending on the spacing, your zone of influence will vary. It will be of near field stress or the far field stress. The first important term or the important term which you may not know about, the well stimulation. Stimulation means you are going to increase some of its property by injecting something, by doing something extra, okay. Suppose the hydraulic fracturing, if you talk to a petroleum engineer, hydraulic fracturing is their core mechanism. You have also know about the hydraulic fracturing. What we are going to do, we are putting water pressure and we are going to create the fracture, the fresh fractures into the coal system. What does it mean? The more we increase the fracture, the more permeability is going to be imported, the more permeability will be increased, okay. So the more permeability and the more gas production rate will come. This is called the stimulation. You are stimulating, you are insisting the reservoir by applying the pressure to increase some of its property, here the permeability. So that's why it is called the well stimulation. You are changing well condition, the degree of well stimulation. So how much you are going to put the water pressure, how much you require the water fracture network, okay. That is also going to be important for your production. So today I'll stop here, okay. If anybody is having any question, any problem for understanding, so please ask me the question. Is it okay for you to understand? Okay.
Yes, sir.
Okay.
Sir,
So yes, tell me any questions.
sir, you have said that earlier that with initially only water will come, but today
Yes.
you have said that increase in gas is also steeply increasing.
No, no. Okay.
Both are
Let me.
contradictory.
Okay, okay. Let me show you again. See that figure? You can see that figure? Okay. See, the production is starting from the zero, whereas the water production is coming very high at a constant rate. You have to understand that in the first place, the moment you have started the gas production, the moment you have started the reducing the pressure, first the water will come, because gases are not in a free state, they cannot come out. It is only after a certain reduction the gases will start to dissolve and then they will come for the production. Okay, now here you can see in this graph, the phase one is given in such a small window, and you may find that, okay, at the same time the gas production is going to be started. No, gas production is just, this period is not like that much of small, because try to understand, all the gases are stored in an adsorbed state. And in the isotherm process, you have also seen that the isotherm, there is a critical resorption pressure. Until and unless you have done pressure, you have put the reservoir pressure below the desorption pressure, the critical desorption pressure, no gas particle will be dissolved from the pore spaces. So after only significant pressure decrease, only the gas production will start. So first is always the water production will come. There may be a certain point when the gas production is started and the with water particles, gases are also coming out. That may happen. But if you see the fraction, you can see the fraction, you can see this much is your higher water production rate and this much is your water gas production rate. So you can identify that how the fraction is going to vary. Okay. And this is just a graph representation. In the actual field, if you are observing the data, you will be able to understand more clearly. Is it okay for the time being? Because you may not be having
Yes,
a total idea. Okay, okay. So thank you. And tomorrow, so as I have mentioned that I have already taken complementary class. So tomorrow in the first period, there will be no class. So we'll again